So there never has been a more appropriate moment for the phrase, but enough about me. Janet and actually Walter Davidson, who's here, played very substantial roles along with Art May and Larkin Kerwin at the period that Janet was referring to. And we were in a situation where we had the potential for funding in the United States. We had actually won a competition among a number of projects in the United States for them to participate. And at that point, it was necessary for Canada to come to the table. We had very favorable peer reviews at the time, and that was, of course, a very important forerunner to all of this. But NSERC and NRC stepped forward, represented by Janet and Walter in a number of cases, but also by the presidents of the agencies. And we were then able to say Canada, in fact, has a major stake in this project, and we won that competition in the United States and got a substantial contribution there as well. It was a lot of work by a lot of people to bring together a project back in those days. It's actually a testimony to where Canada has developed in terms of its ability to do science, to recognize that in 2003, when we were looking for the funding for SNOLAB, we actually had a peer-reviewed competition from CFI that enabled us to simply do what you're supposed to do, put forward your best ideas and have them reviewed by your peers for funding, which was approximately the same amount as we were looking for SNO back in 1989 when there was a tremendous amount of scrambling. And so I think Canada's come a long way in terms of generally the climate of science in this country, and I think it's represented also by the, well, for example, in the study of the Council of the Academies on the state of science in Canada, there are some very positive statements about where we are internationally. I think in essentially all the areas in which Canada is participating, our citations are above the world average, and there are a number of other indicators that we're doing very well. We have some things we need to sort out, and I'll say a few words about that at the end, but my topic actually is the science of SNO and SNOLAB. I'll start with that and then move to a few comments on science policy at the end, because this is, after all, a science policy conference. So what you see in front of you is SNO on the left and SNOLAB on the right. SNOLAB is basically an extension of the SNO underground area. Both of them are 2 kilometers underground in Ballet's mine, and both of them are a Class 2000 clean room throughout the entire laboratory, and even cleaner than that in areas immediately surrounding any one of the experiments. So we're able to really have the lowest radioactivity location in the world. And with that excellent situation, we're able to do science that you just simply couldn't do in any other way. If we didn't shield out those cosmic rays, our detectors would glow like the northern lights for exactly the same reason. Those cosmic rays would cause effects that would overshadow the science we're trying to do. With those conditions, we can address very important scientific questions. How does the sun and stars like it burn? Which of course is very important to all of us, because the elements up to iron were created in stars not so different from our sun, and those heavier than iron were created in supernova. So where we come from is very well represented by information like we can get from our sun with measurements that I'll tell you about. We're trying to address the very basic laws of physics because we have opportunities to study particles that are very difficult to study otherwise. And we're now attempting also to discuss what the composition of our universe is and how it has evolved to the present. And how do we do that? Well, first of all, we measure particles called neutrinos, which are not in your normal daily experience, but we'll say more about that in a moment. And now we're also studying dark matter particles, or hoping to be able to observe them by having the best location in the world right now to be to be able to exclude everything other than them. These are also particles that we think penetrate through matter as neutrinos do very easily, and so our next generation of experiments, of which there are a number in this international laboratory, will address the very frontiers of the sensitivity for dark matter. And also we have the ability to study rare forms of radioactivity with half-lives in excess of 10 to the 25 years. But if you collect enough of the material and if you wait for long enough and nothing else interferes, and it's the nothing else interferes that's important in this case, then you can make very fundamental measurements. So hold out your finger and we'll count 1, 2, 3. Okay, 200 billion neutrinos from the sun have gone through your finger during that period of time. Maybe once in your lifetime, a neutrino will stop in your body, change one atom, and unless it happens to be in your eye and it's closed, like many of them here may be by now, you won't see a thing or feel a thing from that neutrino. But neutrinos are very important and fundamental particles. They're produced in enormous quantities in the center of the sun. The sun is powered by nuclear fusion, held in place by gravity. And the neutrinos are very fundamental particles, but they're very unusual. They have no electric charge. Until recently, we weren't sure if they had a mass. And they, along with electrons and quarks, make up the particles that we don't know how to subdivide any further at this point. There are other particles that are representative of the forces of nature, but these are the basic ones that in all cases come in 3 flavors. For neutrinos, we refer to them as electron, mu, and tau neutrinos, or sometimes as Timbit flavors, but in this case it's electron, mu, and tau that we'll talk about today. They only stop if they hit the nucleus or an electron in an atom head on. So for them, atoms are open space. Basically, they can go through a light year of lead with only a 50% chance of having any sort of an interaction because they only feel the weak force. Therefore, they're very difficult to detect, and so their properties have been among the least known of all the basic particles. And so what you have to do in order to try to get information about even these hundreds of billions that come from the sun is have the lowest radioactivity location you can get, and also build a detector the size of a 10-story building to count 1 neutrino per hour, and you just have to make sure that you don't count anything else at 1 per hour that might interfere with it. The standard model, which as you know has been very successful, and one of the final confirmations has been the identification of the Higgs boson recently, postulated that they have 0 mass and do not change from one flavor to the other. So that was what we set out to examine with our experiment. I'll tell you about some of the advantages we had here in Canada that enabled us to do it. Just to put you in the overall picture, this is the so-called standard model for elementary particles. There are quarks and so-called leptons that are represented by neutrinos and electrons. So up and down quarks, as you see on the left, are what make up in quantities of 3 the neutrons and protons that then make the center of our atoms, the nuclei of our atoms, and the electrons then are what goes around it. There are heavier versions of these that have been observed in particle physics experiments. Neutrinos are unusual. They are really only produced in certain types of radioactivity, particularly what's called beta decay, and they are also produced, as I said earlier, in the nuclear reactions that power the sun. And they really are involved in a process where one quark changes into another quark. The standard model, as I said, postulated them to have 0 mass, but we have shown that that is in fact not correct. The way in which we've shown it is by showing that they change from one type to the other. That is a process that couldn't take place if they were moving at the speed of light, which would be what they would be doing if they had 0 mass, and therefore one knows that they have a mass which is not 0. So why is it important? Why should we even care about these neutrinos? Well, there's a number of reasons that I've tried to list on here. The first 2 on that list I got a little bit of out of order and mentioned already. We come from the processes in the stars and in supernova. And supernova, as far as we know these days, don't even continue to explode if it isn't for the effects of neutrinos in the process of a supernova explosion. The sun is a very interesting star, our nearest star, and it's something that we've been able to study very well using neutrinos because they penetrate easily out from the core of the sun. No problem for them to get here and also to get to our detectors underground. And what we're studying there is fusion. And that fusion process is essentially identical to the fusion process that people want to use to try to create fusion power here on Earth. What we've been able to show with our measurements is that the calculations that are done for the numbers of neutrinos produced in this fusion process are very accurate. And therefore, it gives you hope that the same types of calculations done for the specific case of confining things magnetically rather than by gravity have some hopes of being correct. And it's a very prime example of how you set about to do a basic science experiment, but you're testing the laws of physics. And the laws of physics have very general applicability. And so that's the laws that you're going to use to calculate nuclear fusion, the laws you're going to use to calculate how the sun burns. The fact that that we're able to confirm in one case very accurately that the calculations that are being done are right gives you hope that in other cases of more practical nature on Earth that it's also true. They are produced extensively in the Big Bang. If they have even a small mass, then they affect how the stars and galaxies are created back in the early universe, a very important question. I've already mentioned neutrino astronomy from the point of view of studying the sun. We also have observed neutrinos from supernova, and now there's a program, particularly the ice cube detector under the ice at the South Pole and Terry's experiment in the Mediterranean, that is seeking to use neutrinos to study the farthest reaches of the universe because they aren't affected by intervening matter or magnetic fields and so on, so they really are straight-line messengers. So understanding the properties of neutrinos has a variety of advantages in many areas. The particular question that we set about understanding was a puzzle that had come forward where the calculations of how many are produced in the core of the sun, same ones that, as I say, we now know are very accurate, were not what was being observed in the experiments. But those experiments were ones that only observed the type of neutrinos produced in the core of the sun. And therefore, the question was, were they, for example, changing into one of the other types, which would have been against the standard model of elementary particles, or were the calculations incorrect? So what we needed was an experiment where you could measure both, specifically the electron neutrinos that were being produced and all neutrinos, so that even if they changed into other types, you would know what the total number was. And so that's what we were able to do using a very unique Canadian resource, heavy water. It turns out that with deuterium in the nucleus of the heavy water, you're able to observe two different types of reactions that have exactly those characteristics. One reaction which is specific to electron neutrinos, which if you look on that graph, sure enough turned out to be only 1/3 of the total. Another reaction which is sensitive equally to all three neutrino types. And so what we were able to show with with 5 standard deviation, as they say in the field, but less than a chance in 10 million that it wasn't true, we were able to show that neutrinos in fact change from electron neutrinos into the other two types as they travel from the core of the sun to us. And as you can see by the comparison between the blue bar and the solar model at the top, we also had excellent agreement with solar model calculations. That is what the prize is being awarded for, along with measurements that were made in Japan using atmospheric neutrinos and observing changes in the neutrino type as they traverse the Earth. So what do we have to build in order to do this? That's the SNO detector. It's 1,000 tons of heavy water, $300 million worth, borrowed for 10 years for $1. Pretty good leverage in any market, I guess. And we were very fortunate to have AECL, with assistance from Ontario Power Generation, allow us to do that. We returned it all safely in 2007. We also have the advantage of this tremendously deep mine and cooperation originally from INCO and now Vale. We built a detector then that was about 10 stories high, and it has the heavy water in a transparent bubble surrounded by 10,000 light sensors, capable of observing a candle in the moon, I think someone calculated at one point, very sensitive to even a single photon of light, and very careful control of radioactivity. We built this detector with less than the amount of mine dust that you could pile on your thumbnail, less than about a gram of mine dust on all of the 1 million pieces in the detector, by being very careful about everyone's working conditions. We were 2 kilometers underground, as I said, and about a kilometer and a half out from that number 9 shaft you see there. We nevertheless had everyone take a shower when they got there and change into lint-free clothing and control the dust. What you see in the tower on the side there is the CN Tower. If I'm giving this in the United States, this talk, I usually refer to the entire state building, which sounds wrong, but I have it on very good authority from my 7-year-old who, when we were at Princeton, took a school trip to New York and came back and told us that he had seen the entire state building. So getting some 7-year-olds involved in science is one of the things I'm very hopeful about as we go forward. I'm glad to see the education program emphasized at this conference. That's what it looked like as it was being constructed. You'll notice on, you can't see so well in that photo, but you can see in the next photo on the right that everybody's wearing these neat lint-free coveralls, with the exception of Stephen Hawking, who was vacuumed off before he went underground in a sealed mine car that Inco made, of nickel, of course. Stainless, actually, with lots of nickel in it, though. The water systems were developed to provide very low radioactivity water. David Sinclair, who you see in the picture doing the explanation, was responsible primarily for that, and he was also the person who developed SNOLAB as we went forward, the first director, and a very close colleague over the years. We were successful with our experiment because of all the effort of the many people from institutions there. We started with about 16 people, but ended up with 274 authors on all our papers, and also tremendous support from all of the agencies that you see there, and tremendous cooperation, actually. I think it's worth remembering how things were done at that time. We had what was called an agency review committee, which we met with twice a year. We were very transparent with them. They had also experts on that committee of very well-respected people, like Barry Barish from the United States, for example. We had, and also agency people who were keeping a very close track on this project as we went along. I think it's a good model, actually, for major science as we go forward. So where are we going from here with SNOLAB? Nigel can tell you lots about this. I'll just say a couple of brief things. We have a pretty good picture, still a lot of unknowns, but a pretty good picture of how the universe has evolved, starting with the Big Bang and neutrinos, electrons, quarks, and so on in the early stages. We have a big question of where all the antimatter went, because we think the energy at the time of the Big Bang was converted into equal amounts of matter and antimatter. And the antimatter has obviously decayed away. It's something that we hope to understand by understanding further properties of the neutrinos, which we will do by studying so-called double beta decay in a refurbishment of the SNO detector called SNO Plus, and also in other experiments. And another thing that we may be able to address with the SNO Plus experiment is the absolute neutrino mass. We know differences in mass, and we know there is a mass. We don't know how big it is, except for a limit. We know that that limit is small enough that neutrinos are not the so-called dark matter particles that we know make up about 26% of the total energy component in our universe. That's about 5 times as much as us. One of the reasons we know that is that our galaxy doesn't fly apart. If you look at the stars in the outer part of our spiral galaxy, they're going so fast that if it weren't for a lot of non-glowing matter, they would simply go off into space because there's not enough gravity to hold them at the rate that they're spinning. And there are a number of other indications of the properties of the dark matter. And also, of course, there's dark energy, which is one way of representing the fact that, that Einstein's equations for gravity are not totally attractive, that the universe is actually accelerating. But I think we're in a Donald Rumsfeld type of situation. If you remember the quotation, we have a lot of known unknowns still in this field. 95% of the universe we know takes certain general properties, but we don't know specifically what they are. And in particular for dark matter particles, we are looking for the dark matter particles that we know were produced in the original Big Bang because they're what's holding our galaxy together. The people at CERN, and it's very complementary to what we're doing, are attempting to produce them for the first time since the Big Bang, because hopefully there's enough energy to produce them. In either case, we hope to see how they are new physics, beyond the physics that we already understand. SNOLAB is a great lab. You see the new area that has been excavated beyond the snow area, and very well managed by Nigel. And you also see the set of different experiments that are taking place there, many of them from outside of Canada with large Canadian collaborations in many cases, which is exactly what CFI set as a criterion for the SNOLAB program back in 2003 when it was put in place. It was build laboratories where Canadians will attract international participation and collaboration, and that's happening very, very well. So we're addressing dark matter in a number of different ways. SNO+ is addressing double beta decay, and we're looking for supernova. It's a very effective long-term facility. So, Science Policy Conference, I thought I'd say a few things based on my experience over a number of years with SNO. I think there is a value, there was a question about this earlier on, in devoting some percentage of what you're spending your money on to larger scale projects where you really can address things that are of substantial scientific importance. But I think Canada should look carefully at how they do that. I think that understanding whether there are natural advantages to do such things in Canada is a criterion you can use. We had several natural advantages, the mine and the heavy water. I think the idea, for example, for Neptune of exploring the ocean, instrumenting the ocean, is something that is very natural in Canada. The Amundsen icebreaker in the north is also a very natural idea for Canada, and those are the three projects which were funded by the first CFI round. I think that we should also recognize, and a lot of discussion today already, but we should recognize that the things that are in place, CFI and Canada Research Chairs and the others I've listed there, have really made a big difference in terms of the contribution of Canadian scientists on the international stage, particularly in the academic area. We're one of the top cited countries per capita in the world. But it's very important, if we're going to be able to continue that, to recognize that we're at a stage now where, as it was mentioned in this last panel, the operating support has got to match the total that's been awarded with respect to capital. The criterion of about 10% per year for operating of the capital that you put forward is pretty generally accepted. I think that this is true regardless of the scale. I think it's being addressed in a very good way by CFI for the major projects, and to some degree for smaller projects with their new program. But I think we have to look very carefully at things like the NSERC Discovery Grant levels of funding, because there are many people that have either obtained equipment through CFI and should be able to use it very effectively that simply aren't, because they don't have the money for either the technical or even in the case of many individual researchers, students and postdocs to use it effectively. So I think the balance really needs to be reviewed as we go forward. In funding major science initiative grants, and we've been talking about operating lately, I think we really do have to look at a cradle-to-grave philosophy as we go forward now. We've reached the stage where when new projects come forward, we need a mechanism for deciding between them, but we also have to decide where is the money going to come from for the whole project, and not just we'll give the capital and somehow we'll figure out later where the operating is going to come from, because that gets us in a lot of trouble. And I think there also is necessary to recognize that there are risks that come up in these major projects that in some cases are not predictable. And I think the government has got to understand that they've got to keep an eye on things, and where it's reasonable that these were unavoidable, there has to be some reaction to it. And this agency review committee I referred to earlier was a mechanism that seemed to be very effective in doing that. You can't just give the money and say, okay, go do it, if you're dealing with something that's really on the cutting edge. I think that basic science projects should be a very big part of our overall efforts. I think highly qualified personnel coming out of those projects are very important. But we have to recognize that we're having trouble with respect to industry investment, and we have to deal with that. I'll speak about that in a moment. National laboratories, we started with SNO designed at AECL Chalk River, when they had the capability of providing engineering resources to basic science projects. And NRC was a big part of it in the first place as well. In both cases, they are not, at this point, involved in basic science. I think it's important for there to be not such an absolute statement about thou shalt not do anything other than applied science when you're dealing with national laboratories, because I think there's an advantage to the scientists there in being connected with innovation, and an advantage to the whole community to have the facilities that are existing there plugged in broadly across the community. The peer review process, or evidence-based decision-making, is something we have to worry about very substantially as we go forward. I think that the general public should expect that they would see the review of what is being put forward in a free way by scientists be the basis for which decisions are being made, and so that's important. As I mentioned, we have a very small investment in R&D in Canada, and I think we have to take that into account. But I think we're doing very well in our academic research. Let's make sure we don't kill that in the process of trying to get industry to go forward, because I think the combination of the two is what's important in terms of being able to be innovative. We don't need to just have a situation where we fund our own widgets designed in Canada, because there's an awful lot of innovation happening out there in the world beyond Canada, and the combination of academic and industrial partnerships can put that innovation into Canadian projects as well. So it should be seriously considered. And of course, it's very nice to see that this government is planning to appoint a chief scientist with access, we hope, directly to the PMO, so there will be some influence of that particular scientist. So that's something I would certainly applaud. And so my overall message is SNO and SNOLAB. It's a Canadian and international success resulting from collaboration among many elements, and collaboration both internal to Canada and external through international collaborations is something that's very important then, and it continues to be very important. Thank you very much.